Hello everybody, I'm Luca Benini. I'm a professor at ETH Zurich and University of Bologna, and today I'm going to talk about enabling sustainable AI using a open computing platform perspective. We all know that AI is the big word today, but unfortunately AI is power bound from the cloud to the edge. Let's actually see why. On the left-hand side of this slide, you see the evolution of machine learning models. And this evolution has been phenomenal in terms of capabilities, but also in terms of computational and storage requirement. These are increasing both for training and inference by 10x every 2 years. This is not only a problem of the cloud, it's also a problem at the edge. In fact, many of the new capabilities in autonomous vehicles, robots, industrial equipment require AI deployed at the edge, with the same dynamics in model evolution we see in the cloud. Unfortunately, both the edge and the cloud are power bound, and so we need to increase the number of parameters and the number of floating point multiply and accumulate that we need to do with a constant power budget. Hence, we need to improve energy efficiency. On the other hand, the problem is that energy efficiency, due to technology scaling, is actually slowing down with time with the difficulties of Moore's law. And this is actually shown in the gap between the evolution of machine learning models requirements compared to the evolution of CMOS technology capabilities. 10x every 2 years versus 10x every 12 years. So we have a big energy efficiency problem and sustainability problem. So how can we address this? We have to focus on design. And fundamentally, whenever we design a computing architecture, we have to work at multiple levels of integration and of abstraction. The first level is the level of the processing element, where we actually execute the elementary operations, and we have the local storage for the local operands of our operations. And so here we have to innovate in more and more efficient processing elements. We also have to innovate at the chip level, where we integrate thousands of processing elements with local storage hierarchy and on-chip interconnect to actually achieve efficient computation coupled with storage on chip and data motion. Finally, we have also to innovate at the level of the full platform, going above and beyond the chip. And here the keywords are main memory, interconnect, IOs, as well as three-dimensional integration and 2.5-dimensional integration or chiplets. These are all the main areas of innovations that we have to focus on. So, how do we move about that? Now, let's take an example of the leading company in machine learning and AI hardware, NVIDIA. We can talk about really for NVIDIA and for all this business about the renaissance of design. In fact, if you look at how NVIDIA in the last 10 years has achieved more than 3 orders of magnitude improvement in energy efficiency for inference and training in machine learning models, only 2.5x improvement has been given in 10 years by adopting the most advanced technology options. The remaining factors are all due to innovation in design, architectures, and last but not least, the co-design of algorithm with architecture. So we need not only innovation, we also need a very big flexibility in our hardware. And this is where the big challenge comes if you're not NVIDIA, in the sense that you have to innovate in the software, achieving flexibility to support the fast execution of models and algorithms, while at the same time achieving high efficiency. Now, if you are a hardware monopoly, that is probably feasible and easy. But if you're not, then there is the need for an open standard to counter a monopoly. And this is actually where RISC-V comes into the game. In fact, RISC-V is a standard, an internationally recognized standard across the whole world. It's free, and it's also open in the sense that the instruction set can be used and extended to improve its capabilities for specific classes of computations, not last, of course, machine learning. And there are actually multiple examples across the world, Europe, US, China, where multiple companies, like in the example here, Acceler AI, an European edge AI company, TenStorrent, Canadian cloud and edge AI company, and Meta, one of the big corporations in the US, are innovating around machine learning, inference, and training using RISC-V as a building block, processing based on RISC-V as a building block for efficient machine learning in the cloud and at the edge. In addition to that, RISC-V is really accelerating in terms of adoption. Not only it is adopted by industry, but is also heavily supported by numerous organizations that are also publicly funded. For example, the CHIPS joint undertaking in Europe is investing almost $1 billion in RISC-V architecture for HPC as well as for automotive. And there are many other international initiatives, for example, RISE, which is a global initiative involving players from Asia and from US in developing a mature software stack for RISC-V. In addition, there are industrial initiatives like Quintauris that are seeing big guys in the automotive field working on an architecture based on RISC-V. So it's clear that there is a lot of momentum around RISC-V, but let's try to understand how we can actually use this flexible instruction set to improve the efficiency and the sustainability of AI hardware. I would try to move from more abstract level viewpoint. We should be brain inspired. And by brain inspired, I mean focusing on the fact that the brain today our brain is not really a homogeneous compute engine where all the neurons can do anything. It's actually highly specialized compute engines where several areas of the brain are specialized for different type of computations, for example, linked to the sensory systems. So different areas of the brain supervise sensory input with different types of neurons and neural structures, as well as having specialized regions for the higher level reasoning that fuses information coming from sensory types. So the bottom line is that we want to design our chips as heterogeneous engines with specializations that are targeted at the multi-scale to the AI capabilities that we need. Just now, let's join this idea with the concept of RISC-V and see how actually RISC-V can help specializing the processing engines, the processing elements that we need for the computation. You can see here a sequence of instructions, RISC-V instructions using vanilla standard core instructions that can perform an exemplary machine learning type of computation, an 8-bit convolution. You can see how many instructions we need for each iteration of this loop. And many of these instructions have really nothing to do with the baseline computation, which is multiply and accumulate. So by specializing the instruction set and exploiting the by design flexibility of RISC-V, where you can add up instructions that are domain specialized without violating backward compatibility with the more general purpose instructions, we can actually create a new add-on instruction set for RISC-V, exemplified here at the right-hand side, where we actually add instructions that, for example, merge the access to memory with the computation of the multiply accumulate, employ single instruction multiple data paradigms to combine in a single instruction multiple computations in the same cycle, and accelerate the control flow of the loop to actually achieve a massive improvement in execution time. In fact, this loop executes 15 times less instructions than vanilla, giving us a very big performance boost. Now remember that energy is the product of performance by power. So if we get performance boost, that's great, but we need to ensure that the power is not blowing up. In fact, we now need to compare the core with the basic instruction set with the core with the enhanced instruction set. And we can see here, pictorially depicted, that the core with the enhanced instruction set is getting larger, but on the other hand, there is a big efficiency increase. So we have to make sure that the performance increase is better than the power increase that comes with the increased area. And indeed, this is the case. In fact, the complexity increase and the power increase is marginal with respect to the performance increase given by instruction specialization. And here we gain 1 order of magnitude in energy efficiency. So we have shown here that with the instruction set specialization, we can gain up to an order of magnitude of efficiency on between a vanilla RISC-V processing element and a highly specialized RISC-V processing elements. In addition to that, we have to understand the big effort made internationally by many companies and academic institutions to create an open source flow and software environment for machine learning that comes from the top, from architecture independent tool flows and frameworks like PyTorch, and then goes toward the bottom of this plot, toward applications or domain specific and instruction specific or architecture specific optimizations. All these tools are open source. So we have an open instruction set, extensible and open instruction set, that combines its strength with an open software ecosystem to create an open platform, hardware and software platform for efficient machine learning. But this is not the end of it. In fact, we can actually couple open hardware and ISAs, open software and ISA with open hardware. And that's what my project, my platform, Pulp platform, which my group has been working for more than 10 years, have been focusing on. And here you see many cores that we have developed over the years that have these specialization capabilities, coupled with interconnects, networks on chip, as well as acceleration engines, combined into platforms that range from the tiny microcontrollers up to the high performance accelerators, from the IoT to the HPC, all based on open source software and hardware. And what I mean by open source hardware, actually the RTL of this hardware is released with a permissive license for industry and academia, and it's all made available for free so that people can use it to do research, but also to innovate, start their own companies, and they can freely use this open source hardware for commercial exploitation. Now, as an example what open hardware enables, let me just take another perspective on the processing elements. We need simple processing elements in some cases where the focus is only on doing a specific computation, but we also need complex high-performance processing elements like processors, powerful processors. And here you see the evolution from a simple application processor that can run Linux but with a single issue architecture to a multi-issue superscalar architecture developed in cooperation with my team and several European companies, as well as an out-of-order superscalar architecture actually leveraging Yuan T910 designed by T-Head and Alibaba in this combined work that we are now working on, so that we can provide several flavors of course leveraging open source hardware that we develop, but also that other companies and research institutions are developing. So to move ahead, we can innovate at multiple levels. The processing elements that I already described with instruction extensions are a primary way to gather energy efficiency. But in addition to that, we can have more energy efficiency with the accelerators, decoupled accelerators, and tightly coupled accelerators like tensor engines that are shown here in green. So RISC-V is a key enabler across the board for all these capabilities to enable software build-up, no vendor lock-in, and very high agility and programmability. An example of this vision is the Kraken chip. The Kraken is actually an extreme edge brain. It's a tiny chip consuming only a few milliwatts, but it has all these ideas together in there. So the first is the processors with the tightly coupled tensor accelerations the loosely coupled specialized accelerators that you can see here, all in a chip that is a few millimeters squares and consume only a few tens of milliwatts. Now, this chip, implemented in 22 nanometer technology, powered at 0.6 volts, achieved the following efficiency. Moving from 10 picojoule per operation for a vanilla RISC-V core, we can gain one order of magnitude with instruction specialization, as clarified before. Then we can get another order of magnitude by coupling the specialized cores with tensor engines. And finally, by having fully specialized hardwired accelerators, we can actually reach another order of magnitude. So we have a 4 order of magnitude for innovation in efficiency thanks to heterogeneous specialization. It's a large design space that we are far from completely exploiting. Now, to move toward the wrap-up of my talk, we are going to move in the term of AI from the perceptive models to the generative AI models, where the large transformer units are actually producing much more powerful AI capabilities. And finally, to put these large models into everyday devices, robots, cars, and this is what we call embodied AI model. That's the big challenge and the big market for the future. Now, how can we get this type of large-scale architectures into our open platforms? Of course, we need again the help of technology. The first step is, as shown here in this Okami chip that we designed last year, we can pump up the performance by heterogeneous integration based on chiplets, but the future is to go back to the brain and understand that the brain is a truly three-dimensional entity. It's not 2.5D or 2D. And so the real future is when we will get three-dimensional CMOS technology coupled with an architectural platform for the ultimate innovation. And with that, I would thank you for your attention, and thank you again to everybody.